In this video, I want to solve some equations involving exponential functions and logarithms. These problems come from section 3.4, page 490 of our textbook, Robert Blitzer's Pre-Calculus. So let's start off here with number 20. The instructions are: solve each exponential equation by expressing each side as a power of the same base and then equating the exponents. So, I don't know, to me, when I see this problem, this is the approach I want to use because I know 8 and 4 can both be powers of 2. So even if the instructions didn't say to write each side as a power raised to, as a power of the same base, I'd probably do it this way anyway. So let's see, 8 is 2 to the third power, still raised to the 1 minus x. 4 is 2 squared raised to the x plus 2. Raise a power to a power and we multiply the exponents. So I need to imagine multiplying 3 and 1 minus x. Well, I need to distribute, so I get 3 minus 3x. Same thing on this side. I need to multiply 2 and x plus 2, and I'd have to distribute, so I get 2x plus 4. It's in this step where both sides are 2 raised to a power, so I can just equate the exponents. So I want to get all of the x's on one side and all the constants on another. So I'm going to add 3x to both sides and I'll get 5x. Take 4 away from both sides and I would get a minus 1. So I get x equals minus 1/5. All right, and we could actually take a minute to check our answer by plugging it into the original equation. I think that's a good thing for everyone to do. You could in fact pause the video here to check that answer. But I'm going to move on to question number 22. Question number 22 says that e raised to the x plus 4 power is 1 over e to the 2x. So on this side I can leave it alone, but on this side I'll rewrite it with a negative exponent. 1 over to e to the 2x is e to the minus 2x. And now we can equate the exponents. All right, let's take x away from both sides. So I end up with a 4 equals minus 3x. Divide by minus 3. And I find out that x is minus 4/3. All right, so we solved 2 exponential equations. In the next set of problems, the instructions change a bit. But again, I think the instructions could just say solve, because my approach is kind of dictated by the problem here. But we're told to solve each exponential equation, express the solution set in terms of natural logs or common logs, then use a calculator to obtain a decimal approximation correct to 2 decimal places. All right, so I need an exact solution and I need a rounded solution. So I have my TI-84 on hand for the rounded part. All right. There's no easy way to get 3 and 7 to the same base. If I was going to imagine that, I'd need to use logarithms. Anyway, so my approach to solving this exponential equation is to take a natural log of both sides. So I take the natural logarithm of both sides, and now I can rewrite the exponents out front. And this is actually why we're doing this, because now I have 2x plus 1 times a number, the natural log of 7, equals x plus 2 times a number, the natural log of 3. And that's how I want to think about the natural log of 7 and the natural log of 3. I do not want to round them here. The instructions tell me to get an exact solution in terms of logarithms, so I can't just round them here. But they are numbers, so I'll treat them just like any other number. So I need to distribute on both sides, and then I'll have to get the x's together and all the constant terms together. So I'm just distributing, treating the natural log of 7 and the natural log of 3 like they're numbers, because that's what they are. All right, so let's see now. I need to get the things with x's together. So I'm going to imagine taking away the natural log of 3x from both sides. So So I have 2 times the natural log of 7x minus the natural log of 3 times x. And now I'm going to subtract the natural log of 7 from both sides. All right, and I need to be a little careful here, right? Where I did this, that was 2 times the natural log of 7 as a number, all times x. This is a natural log of 3 times the variable x. So that's just the coefficient in front of x. This is just a different coefficient in front of x. So what I see on this side now is I could actually imagine factoring out an x. All right, so now I can get x by itself by saying that 2 times the natural log of 7 minus the natural log of 3, all over 2 times the natural log of 3 minus the natural log of 7. That's a nice, happy, exact solution. Now I'd like to find a decimal approximation, ran to 2 decimal places like I was asked for. So 2 times, well, let's be careful here, 2 times the natural log of 7 minus the natural log of 3. And I'm putting the numerator here in its own set of parentheses. Divide by the denominator, which will also be in its own set of parentheses. And let's see, I get 11.11. And there's our nice, happy, rounded solution. All right, so that took care of number 42. Now we're asked to solve number 47. (47) is an exponential equation that is in a quadratic form. So I'm going to start by imagining factoring it. 3x times 3x would give me a 3 to the 2x. And now I need things that multiply together to give me minus 2, but have a difference of 1. So let's see, I think that's going to be a plus 2 and a minus 1. All right, well, this is kind of nice because now I can set this part equal to 0. 3 to the x plus 2 equals 0. And just for a moment, I'd have 3 to the x equals minus 2. Well, if I raise 3 to a power, I can't get anything less than 0, so there's no solutions there. And this one gives me 3 to the x minus 1 equals 0, which is just 3 to the x equals 1. What power do I raise 3 to get 1? Well, we could do some equation solving stuff, but that's 0, because anything to the 0 power is 0. There's my exact solution. I don't think there's a need to round that to 2 decimal places. It doesn't get any better than that. Well, we've solved 4 exponential equations. Now let's solve 4 logarithmic equations. Here are the instructions. Be sure to, solve each logarithmic equation. Be sure to reject any value of x that is not in the domain of the original logarithmic expression. Give the exact answer. Then, where necessary, use a calculator to obtain a decimal approximation. Correct to 2 decimal places. All right, here in number 78, I have the log of 5x plus 1 is equal to the log of 2x plus 3 plus the log of 2. Since I have logarithms on both sides, I think I'm going to use the one-to-one property. So if I condense this to a single log, I'll be able to set the insides equal to each other. All right, so I need to multiply these two things. I'm just going to go on and imagine distributing. So 4x plus 6. Now that I have a log equals a log, the one-to-one property says I can set the insides equal to each other. 5x plus 1 is equal to 4x plus 6. Take 4x away from both sides, I get x equals. Take 1 away from both sides, and I find out that's 5. I need to plug that back into the insides of all the logarithms. Make sure that it's in the domain, that I don't get 0 or a negative value. Well, that's going to give me a 26 on this side. Plugging in here, I'd get a 13, and I'll have to worry about that one because it's always a 2. That one works just fine. And that takes us to number 80. Another problem that looks a lot like the one we just solved. Another problem involving a log base 10. So again, we need to condense the right-hand side. And so I'd have 3 times x plus 3. And on the last one, I just went undistributed. But on this one, I decided to show some work. No real reason why. All right. And again, I have a logarithm equal to a logarithm. We can set the arguments equal to each other. So I have 2x minus 1 equals 3x plus 9. Take 2x away from both sides, and I would get x. Take 9 away from both sides, I get a minus 10. And if we were not paying attention, we might try to move on to the next problem, and we'd get this one wrong. Because we need to try to substitute back in, and when I do, I get 2 times minus 10 is minus 20. I get a minus 21 here. That's not in the domain of that logarithmic expression because I get a negative on its inside. It's also not in the domain of this one, but failing once is enough. This is a sad moment where we get an empty set. That's the symbol for the empty set. There's no solutions here. And that always just makes me a little sad when I have an equation with no solutions. It also makes me a little happy because it's cool. But 2 more problems to go. Let's see what happens. Numbers 90 and 91. All right, so again, I have logarithms on both sides, so I think I'll condense both sides. There we go, number 90. Condense the left-hand side, this side's already condensed, and then solve the resulting equation I get when I set the insides equal to each other. So we end up with x minus 1 over x plus 3 equals 1 over x. All right, this was a logarithm base 2. In the end, it doesn't really matter because the insides being equal is what we really need. And so if we change those bases to any base, we get the same resulting equation. So we can clear this equation of fractions by multiplying by the least common denominator. Most students these days call that cross multiplication. We end up with this. On the left-hand side, when we distribute, we get x squared minus x, and then equals x plus 3. Let's get everything on one side, because this is a nice, happy quadratic equation. All right, and it's a quadratic equation that appears to factor nicely. So x is equal to 3 or minus 1. I can throw away the minus 1 very quickly because it's not in the domain of this logarithm or this one. And failing once is enough, so just not being in that domain is enough to get rid of it. X equals 3 seems to work just fine. I end up with a 2 here, a 6 here, and a 1/3 there. And everything seems to check out just fine. So there's my one solution. And that'll take us to question number 91. Which involves the natural logarithm. And on the left-hand side, I have the natural log of x minus 2 minus the natural log of x plus 3. And on the right-hand side, the natural log of x minus 1 minus the natural log of x plus 7. We'll use the quotient rule for the logarithm here on both sides. Set the insides equal to each other. And again, we can solve this by rewriting it as if we've cleared the equation of fractions. And again, that can be thought of as cross multiplication. All right, so let's distribute on both sides. See, a 7x minus a 2x, I get a plus 5x minus 14. On this side, I get an x squared plus 3x minus 1x, so plus 2x minus 3. Take x squared away from both sides, and those will cancel. Subtract 2x from both sides, I get 3x. Add 14 to both sides, and I'll get an 11. I get x equals 11 over 3. I need to check that. Take 2 away from it, I'll get a positive number. Take 1 away from it, I'll definitely get a positive number. and that value is in the domain of all of my logarithms, so there's nothing wrong with it there. So now I've done all the problems from the textbook that I wanted to do, but I want to do one more quick example. So just one more example. So let's say someone asked me to solve the log base 3 of x minus 2 plus the log base 3 of x minus 1. Let's just say that was equal to a constant. I don't know, like 2. All the examples I picked from the textbook here involved having logarithms on both sides where I could use the one-to-one property. On this one, I could use the product rule for the logarithm to get to here. And now what I need to do is rewrite this as an exponential statement. So the inside, x squared minus 3x plus 2 would equal 3 squared, the base raised to its exponent. So let's see, that would be x squared minus 3x plus 2 is equal to 9. Take 9 away from both sides and we get the quadratic equation x squared minus 3x minus 7 is equal to 0. And just under a quick inspection, I don't think this is going to solve very nicely by factoring, right? Because there's nothing that multiplies together to give me 7 that adds up or subtracts to give me 3. So I think I'll need to use the quadratic formula here. X is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So let's see, 3 plus or minus the square root of 9 plus 28, which is 37, all over 2. So right now it seems that I have two solutions, 3 minus the square root of 37 all over 2, and 3 plus root 37 all over 2. Well, the square root of 37 is larger than 6, so this is 3 minus a number larger than 6. This is a negative value. So if I take a minus 2 away from it, it's still negative. That can't possibly be a solution. It's not in the domain of, keep pointing off screen, that logarithm that we started with there. All right, so now let's check this one out and make sure that it's going to work inside that logarithm. So let's get a decimal approximation just to make sure everything's going all right. So 3 plus root 37 divided by 2, that's a number larger than 4.5. So if I take 2 away from it, the inside's still positive. Take 1 away from it, still positive. So there's my nice, happy, exact solution to this one more example.